That is the other things community policy. currently checks starting to.
All right, it's 5:30, so let's go and get started. All right, good evening, everyone. How's everyone doing? And have a good spring break? Good, good. All right, so last time we were here, we were kind of rudely interrupted because Cal State Fullerton doesn't want to pay his power bill. So hopefully that's not going to be an issue today. Hopefully we can finish the lecture. So we kind of stopped right in the middle of an example last time. So first thing we're going to do today is we're going to just kind of pick up right where we left off. Before the spring break, we're going to finish up that example. We're going to finish up these lecture notes. We have one more topic to cover, which is Gauss quadrature. And then we're going to move on to kind of the final kind of big topic in this class, which is 2D finite elements, which is going to be the topic of your final project as well. Okay. So speaking of your final project, so next week on Tuesday, I plan on going over the details for that final project. So I'm still kind of formulating the project a little bit, kind of formatting and changing up a little bit. And I think probably it'll make a bit more sense next Tuesday once we kind of get to that point. So today, what I want to do is kind of finish up the theory in terms of 1D finite elements, talk about Gauss quadrature. And then on Thursday, we're mostly going to be talking about the MATLAB implementation, right? So Thursday is kind of the last day that we're going to do kind of a full kind of code walkthrough together. And so, we'll walk through together how to implement the 1D equations in MATLAB. And then essentially what your final project is going to be is to implement a 2D solver with generic finite elements, and get that working in MATLAB and doing some tests and writing reporting. Okay. Okay, so that's the plan for today. So, for the rest of the semester, so we don't have that much time left. So we have about 5 more weeks of instruction, including this week. And so in that time, we're going to take another midterm exam. And so that's going to be close to near the end of the course. So that's going to be week 14. We're going to, and then we're going to work on the final project from there. So it'll be a little bit, so next few weeks are going to be pretty busy. So I expect, there's going to be quite a few things to work on, but, we'll get there. Okay. All right, so the other announcement that I want to make that probably a lot of you noticed over spring break was that I did post the next homework assignment. So numbering wise, because we had the 2 ANSYS activities, this is technically only homework set 2. Okay. So homework set 2, this is based on a lot of what we've been covering so far. So this is on strong forms, weak forms, and the last topic for this homework is finite element forms. Okay. Which we're going to finish up today. So you should have everything that you need to complete probably the first 3/4 of the homework assignments, because we've already covered strong forms and approximate solutions to weak forms. And then after today, you'll have everything that you need to cover for the finite element form. So this is going to be due this Sunday, which is April 14th. Okay. Okay, so definitely, if you haven't gotten started on it yet, I would definitely take a look. These problems aren't, I think, they're not that difficult, and in fact, they're a lot less tedious than the direct stiffness problems, just because the matrices aren't nearly as big. But it still can take some time. So you definitely want to make sure you get a good head start on that stuff. Okay. All right. Any questions on anything before we get started for today? Okay. All right, so let's pick up right where we left off. So I'm actually going to go back to our week 10 lecture notes. Okay. Okay, so let me kind of scroll up here just to kind of show you our problem. Okay. So before the power outage last third, or before the spring break, we were doing this example problem here. So we had a 1D situation. So we have a rod that's subjected to a compressive force. Okay. It's going to be fixed on the left-hand side, and we have a body force, a constant body force of 2 Newton per meter. Okay. And the other caveat that we have for this problem is that our area is going to be changing as a function of x. Okay. So actually, if I were to draw this this rod a bit more accurately, you know, it would look something like this. It would kind of fan out, you know, near the. So it's wider on the right side than it is on the left. Okay. So I picked this problem just because, you know, this is something that, you know, we wouldn't actually be able to solve with direct stiffness because first of all, we have an area that's kind of smoothly varying throughout the entire member. And we have a body force term, which is something that's new. Okay. So this is a situation, you know, we can't just tackle this with our usual truss elements. We have to solve it directly from the differential equations, you know, because of how it's designed. Okay. And then what we said was that we want to find a finite element solution to this problem using a 2-element system. So we have one element that goes from x is equal to 0 to x is equal to 5. And then the second element goes from x is equal to 5 to x is equal to 20. Okay. All right, so our methodology or kind of the way we're going to solve this problem is we're going to form the element stiffness matrix and the element forcing vectors for every element, and then assemble it all together at the end. Okay. So this is the this here is our equation for the element stiffness matrix. So if you recall from before the spring break, we take the integral from the left-hand side of the node x1 to the right-hand side of the node x2. We multiply it by the column that we take the column vector of the shape function derivative, d1 dx, dn1 dx, and dn2 dx, multiplied by e times a times a row vector of the same shape function derivative, so dn1 dx, dn2 dx. Okay. So for our usual case, which is going to be for a linear element, a linear finite element, our shape function derivatives are going to be linear or constant functions. Right. So this part here is pretty simple. And so I think visually when you first look at this equation, I think those shape function derivatives and that matrix form is a little bit intimidating, but just know that the shape function derivatives for the most part are just going to be constant terms. Okay. All right, so you plug those in here and you plug these in here, right? So you have a -1/5, -1/5, okay? We plug in our value for E, so our value for E here is 5,000 Pascal. And then we're going to plug in our function for the area as well, which is 1 plus x squared over 400, okay? All right, so we perform that arithmetic, right? So we take everything here. We notice that a lot of this here are just constants, so we're just going to factor those out of the integration. So we have a 5,000, that, and then we have our matrix here, -1/5, -1/5, 1/5, 1/5, so on and so forth, okay? So we perform all that math. And on the outside of the integral, we get this matrix of 200, -200, -200, and 200. Okay. And then the integral itself, we're just going to be performing integral from 0 to 5 of 1 plus x squared over 400 dx. Okay. And so we evaluate that integral, we get x plus x cubed over 1200, evaluated from x is equal to 0 to x is equal to 5. And we multiply that factor through the entire matrix. And then what we get is this 2 by 2 matrix. So this is the element stiffness matrix of element A. Okay. So you have 1020.83, -1020.83, -1020.83, and 1020.80. Okay. All right. So that's our first element stiffness matrix. And so we're going to keep hang on to that. Okay. The next thing that we have to do, and this is something that's new. So this is not something that we had to do before for our direct stiffness problems, was we're going to evaluate an element forcing vector. Okay. All right, so if you recall from last time, our element forcing vector has the following equation. We have Fe is equal to integral from x1 to x2 of n1 of x. It's the ugliest n I've ever drawn. N1 of x and 2 of x. Okay. Times the body force term b of x dx. Okay. Plus the Neumann boundary condition term. Okay. So plus quantity n1 of x and 2 of x times a times t bar. Okay. Evaluated at x is equal to the Neumann boundary. Okay. Okay. So a couple things with this expression. So obviously we have two different terms here, right? So this first term here, this is our body force term. Okay. How do I know it's a body force term? Because it involves our function b of x. So that almost always has to be integrated. And so if you have a non-zero b of x, then you have to integrate that term for every single one of your elements. Okay. And then the other term that we have here is the Neumann boundary condition term. So any kind of loads or any kind of forces get evaluated in this term right here. Okay. All right. So one important note, this second term right here, the Neumann boundary condition term, we only evaluate this term if our element borders a Neumann boundary. Which for most cases is not going to be true. So in 1D, you're only going to have one element that borders the Neumann boundary. And so you're not going to evaluate that term for every single element. Okay. And so if we look back at the geometry of our problem, so let me kind of scroll up here for just a second. Okay. If we look at the geometry of this problem, our Neumann boundary condition is being applied on the right-hand side of our domain. Okay. That means the Neumann boundary condition is being applied right here at x3. Okay. But we're not on element 2 yet. So what we're doing is we're evaluating the element stiffness matrix and element forcing vector for element 1. Okay. And so for now, since we're on element 1, we're not going to evaluate this term right here. So we're just going to ignore this. Okay. Okay. So the only term that we're going to be evaluating here is just this first term here. Okay. So let's go ahead and plug in for these guys. All right. All right, so let's remind ourselves kind of what gets plugged into each of these terms here. Okay. So first we have the shape function. So we have n1 of x. Okay. We know n1 of x is equal to x minus x2 divided by x1 minus x2. Okay. N2 of x, that's our second shape function for our linear element. This is equal to x1 minus x divided by x1 minus x2. Okay. And then we know b of x. B of x in this case is just a constant. And so b of x here is just going to be 2 newtons per meter. Okay. Okay. So knowing all of these things here, let's go ahead and plug all those in. And oh, by the way, we also know for this element, x1 is equal to 0 and x2 is equal to 5. Okay, so let's plug all those in. So Fe for element 1 is equal to integral from 0 to 5. We have a column vector of n1 and n2. So we have x minus x2 divided by x1 minus x2. Okay. Then x1 minus x divided by x1 minus x2. Okay. Our b of x here is just 2. And we're integrating with respect to x, or dx right there. Okay. All right. So let's simplify this a bit. So I know I've already plugged in for x1, x2 for the integration bound. So let's plug in for x1, x2 for the for all of the interior parts there as well. Okay. Keep in mind that we have a lot of constants here, and so if it's a constant, we can just pull it out of the integral. Okay. So both n1, n2 have this 1 over x1 minus x2 factor, right? And so that's going to be 1 over 0 minus 5. So that's a -1 thing, okay? So I'm going to pull that factor out from the integral, and I'm going to pull the 2 out as well, okay? So this is going to be equal to minus 2 over 5 integral from 0 to 5. We have x minus x2, so that's x minus 5. And then we have x1 minus x. And so that's going to be 0 minus x dx. Okay. Which, if you just want to be simple, is just going to be minus x. All right. So let's go ahead and perform this integration. So we're going to integrate both terms. Again, it may look scary to kind of combine, we were basically combining linear algebra and calculus here, but the integral is basically just an operation that applies to each entry of a vector or each entry of a matrix as we see. Okay, so we're just going to integrate the top term and then integrate the bottom term. Okay, so we have a -2/5, can't forget about that. And then the integral of the top term there is going to be x squared divided by 2 minus 5x. And then integral of the bottom term, which is minus x, is going to be minus x squared over 2. Okay. And we're going to be evaluating this between x is equal to 0 and x is equal to 5. Okay, so let's go ahead and plug in for this. And so we have we're going to evaluate everything at x is equal to 5 first. So if we evaluate the first term in the vector, so that's 5 squared divided by 2 minus 5 times 5. Okay. And then we have minus, we're going to evaluate everything at x is equal to 0. So we have minus 0 squared divided by 2 minus 5 times 0. Let's do the same thing on the denominator. So we have minus 5 squared divided by 2 minus 0 squared divided by 2. All right. So let's go ahead and simplify this. So of course, everything that's evaluated at 0 is just going to be 0. So it's going to cancel those out. Okay. And if we evaluate both terms right there, we have -2/5. Up top, we have a 25/2 minus 5 times 5, which is 25. And so that's going to be minus 25/2. Okay. And on the bottom, we have a -5 squared/2. So that's going to be another -25/2. Okay. All right, so let's simplify this. We're going to multiply every entry in that vector by -2/5. The negatives are going to cancel out, the twos are going to cancel out, and we're going to divide 25 by 5. And so this just is equal to 5 and 5. And this is our element forcing vector for element. Now let's put this together with our element stiffness matrix. So what we computed before. Okay. And we have our full elemental system for element 1, element stiffness matrix and element forcing vector. Okay. And so our system here is 1020.83 minus 1020.83 minus 1020.83, 1020.83. Okay. Element A in this case is connected to nodes 1 and 2, so that's going to be U1, U2. Is equal to our element forcing vector, which is just 5 and 5. All right. Any questions on how we got this this result here? Okay, good. All right, so let's do the exact same thing for element 2. Or I guess element B. Okay. So just like element A, we're going to compute the element stiffness matrix and the element forcing vector. Okay. So let's start with the element stiffness matrix. So we have KE is equal to integral for x1 and x2 of dn1 dx, dn2 dx times E times A times dn1 dx, dn2 dx, dx. Okay. All right, so now it's just going to be kind of another plug and chug. But one thing you have to be careful of is that when you're performing these integrals here, and when you're evaluating your shape function derivatives, you have to note that every element, the x1 and x2 are going to change. Okay. Now, when you're plugging in here, x1, what we refer to x1 in this equation, in these equations, that refers to the coordinate of the left node of the element. Okay. You could say that it's also the lower node or whatever. Okay. And x2 here is the coordinate of the right node. Okay. So for our first element, our first element was bordering kind of the left boundary, right? And so if you notice for the first element here, we said x1 is equal to 0 and x2 is equal to 5, right? And so if we come back to our diagram here, we can see for element 1, the left node is 0, the right node is 5. Okay. Now we're doing element 2 or element B. Okay. So now the left node here is 5 and the right node here is 20. Okay. So when we come back to this here, right? This means we're going to set x1 in our equation equal to 5 and x2 is equal to 20. Okay. So that x1, x2 there, it's relative to whichever element that you are considering. Okay. So these change based on the element. Okay. So you want to be careful about that. And so, and I know the terminology and the symbols kind of make it a bit confusing because I use x1, x2 for a lot of different things. But just know that when you're plugging into the formulas for the element stiffness matrix and the shape functions and the element forcing vectors, that's kind of what these x1, x2 are referring to. Okay. Okay. So that means when we compute our shape function derivatives, dn1 dx, okay, we know this is equal to 1 over x1 minus x2. Okay. If we plug that in for this particular element here, this would be 1 over 5 minus 20, which is a minus 1 over 15. Okay. And then dn2 dx is equal to 1 over x2 minus x1, which is equal to 1 over 20 minus 5, which is a positive 1 over 15. Okay. If you compare that to the first element that we considered, the shape function derivatives were 1 over 5, right? Because that element was a lot smaller. But since element B here is much bigger, that means our shape function derivatives are going to be different as well. Okay. Okay. So let's plug all that in. So our KE, or element stiffness matrix for our second element here, is going to be integral from 5 to 20 of column vector minus 1 over 15, 1 over 15 times E. We know E here is 5,000. Our area function here is 1 plus x squared over 400. Okay. And then our other shape function vector here is minus 1 over 15, 1 over 15 dx. All right. All right, so let's simplify this. So let's do our algebra. So let's multiply these vectors together to get a matrix. Let's take our 5,000. Let's factor it out. Okay. So if we do all that, so I'm just going to skip a few steps right here. We get 200 over 9 minus 200 over 9 minus 200 over 9, 200 over 9. Okay. Multiplied by integral of 5 from 5 to 20 of 1 plus x squared over 400 dx. Okay. All right, so all I did there was I just multiplied the vectors together, got my 2 by 2 matrix, and then multiplied the entire thing by 5,000, and you get 200 over 9 from that. Okay. Skipped a couple of steps, but just want to make sure we get through this today. All right, so we evaluate that integral, and so that integral is actually the same expression as it was before. Okay, so let me go ahead and bring down our matrix here. And so we get x plus x cubed over 1200, evaluated from x is equal to 5 to 20. Okay. And so if we evaluate that, that just ends up being a constant that we're just going to multiply all throughout. Okay. And so our element stiffness matrix for the second element is going to be 479.17 minus 479.17 minus 479.17, 479.17. All right, any questions on that? Okay. All right, good. All right, so next we have our element forcing vector. So just like we did before, let me go ahead and write out the full expression for the element forcing vector. So FE is equal to integral from x1, x2 of n1, n2, b of x dx plus quantity n1, n2 of a t bar evaluated at the Neumann boundary. Let's go ahead and just plug in everything here. So we know that n1 and n2, that's their expressions are going to be different because of our different nodes here. Okay, so this is going to be a minus 2 over 15 integral from 5 to 20 of quantity x minus 20 5 minus x dx. Okay. Plus our Neumann boundary term. So we are going to actually evaluate this term here because our second element does border the Neumann boundary. Okay. So that term there is actually going to be non-zero. Okay. And so for this particular element, the Neumann boundary is located at x is equal to 20. Okay. So everything that we have in those brackets there, we're going to evaluate it at x is equal to 20. So that includes the area function, which we know is going to vary. And that includes the shape functions as well. Okay, so let me show you what I mean. Okay. We'll come back to the integral in a second. This part here is important. Okay. So we know n1 is equal to x minus 20 divided by 5 minus 20. And n2 is equal to 5 minus x divided by 5 minus 20. Those are just the values of our shape functions with the coordinates kind of plugged in, x1 and x2. Okay, so let's evaluate these. Let's plug in x is equal to 20 into each of these. Okay. So we're going to plug in x is equal to 20. X is equal to 20. Okay. So we plug in x is equal to 20 in the top one. We get 20 minus 20 over 5 minus 20. And so we get 20 minus 20 up top, which is 0. 0 divided by anything is just 0. Okay. And then on the bottom there, we get 5 minus 20 divided by 5 minus 20. We have the same thing on the top and the bottom. And so this is just going to be equal to 1. Okay. And so that term there in brackets here is going to be 0 and 1. Okay. We have our area function. Our area function is 1 plus x squared over 400. And so we have 1 over 20 squared over 400. And then we're going to multiply that together with the with a stress term, which is -5. And so we perform this out, we get a vector here. Top term is going to be 0 because 0 times anything is just 0. And then on the bottom there, we have a 1 times 2, okay, because the area function 1 plus 20 squared over 400, that's just going to be 2 times 5, which is going to be -5. Or excuse me, -5 times 2 is -10. Okay. So this right here is the contribution to the element forcing vector from the Neumann boundary. So notice we only get a contribution on the second node, which makes sense because that's where the Neumann boundary condition is being applied. Okay. All right. Any questions? Any questions on how we got that? How we got that term there? Okay. All right. So the other thing that we're going to do is we're going to evaluate the integral here. So I kind of left that hanging there. Okay. So let's go ahead and evaluate this integral now. Okay, so we have a -2 over 15. Let's evaluate the integral on both of those terms. So we have an x minus 20. So that's going to be x squared over 2 minus 20 x. And on the bottom there, we have 5x minus x squared over 2. Okay. We're going to evaluate this from x is equal to 5 to x is equal to 20. And so if we do that, and so this is just kind of standard just integration here, and then what we get, and after we multiply it from the outside, is what we get is 15 and 15. All right. So now we have the contribution to the element forcing vector from the body force. We have the contribution to the element forcing vector from the Neumann boundary condition. And so now what we're going to do is simply add these two things together. Okay, we have a 15, 15 plus 0 minus 10. And so that means our element forcing vector for the second element is going to be 15 and 5. Okay, so let's put it together with the element stiffness matrix that we found for this element. Okay. And so our entire elemental system for element 2 or element B is 479.17 minus 479.7 minus 479.17, 479.17. Okay. U2, U3 is equal to 15 and 5. All right, any questions on how we obtained that result there? Okay. All right, so now that we're done with the elemental systems, from here it's pretty straightforward, right? So the biggest difference, I would say, between what we're doing now compared to the direct stiffness method is how we form these element stiffness matrices and element forcing vectors, right? So in the direct stiffness method, we kind of shortcut this method here where I just kind of gave you formulas to plug into. Granted, they were extremely tedious formulas to plug into, but they were kind of plug and chug. With these kinds of problems here, there's a little bit more work involved. So you actually have to perform some integrals, and sometimes multiple integrals per element. Okay. But from here on out, it's the same thing. So now that we have the element stiffness matrices and the element forcing vectors, the next step is to assemble these into a single system, apply the boundary conditions, and solve. Okay. So these next few steps here, I'm going to go through fairly quickly, just because we've seen this kind of a million times already. Okay. So the next step here is going to be assembly of the elemental contributions. Okay. And so if our system right now is a 3-node system, right? So let me go ahead and draw it here again. Okay. So we have node 1, node 2, node 3. Okay. And since this is purely just a one-dimensional case, that means our global stiffness system is going to be 3 by 3. Okay, so let's go ahead and draw that out. So our 3 by 3 global system looks like the following. We have U1, U2, U3, U1, U2, U3 is equal to F1, F2, F3. Okay. So let's do the same thing that we've always done, in our direct stiffness system. Let's assemble these contributions. Okay, so let's start with element A. Okay, so element A we know is connected to nodes 1 and 2. Right? This is element A. Okay. So element A is going to be this section right here. Okay. The other thing that we're going to have to do now is we have to assemble the element forcing vectors as well. So it's gonna take up that portion there as well. Okay. Our other element here is element B. Okay. And we know this is going to be nodes 2 and 3. It's going to be this portion here and this portion right here. Okay. Notice how their elemental forcing vectors overlap on node 2. Okay. Okay, so let's go ahead and input the values for those. Okay. And so we input the values for these, we get 1020.83 minus 1020.83 minus 1020.83. Okay. And the two parts where they overlap, we're going to sum them together. So we have a 1020.83 plus 479.17. Okay. And then all the other entries for element B there, we have 479.17. Okay. Everywhere that we don't have anything, we can just fill in. Okay. Fill in zeros. Next, we have the element forcing vectors. And so the element forcing vector for element A is a 5 and a 5. And then the element forcing vector for element B is a 15. 15 and 5. So we're going to have a plus 15 and then a 5 up there. right. So hopefully this part here is pretty familiar. So it's basically just kind of the same assembly system. Okay. So the last thing we have to do before we can solve is apply our constraints or apply our Dirichlet boundary conditions. Okay. So in this case, we're going to apply our fixed constraint on node one. So our equation for that is U1 is equal to 0. And so that means that the first row in our matrix here, we're going to replace that just like we did with direct stiffness. Okay. And so we're going to replace that. Let me kind of erase these guys here. And so if we erase that, we get 1, 0. And on the right-hand side, we're just going to get 0. Okay. Let me go ahead and sum everything that needs to be summed here. And so in this middle part here, we have those two things add up to 1500. And on the forcing vector side, those two things add up to 20. Okay, 15 plus 5. Now that we have the system in this form, we are now ready to solve for a solution. And so you can solve this whatever way that you want in your calculator, MATLAB, whatever. Okay. And so if we solve for the solution, we get the following. Let's get U1 is equal to, since U1 is at the constraint, we know U1 is going to be equal to 0. Okay. U2 is going to be 0.245 meters. And then U3 is going to be 0.349 meters. All right, so that last part there, I went through fairly quickly just because we've seen this just so many times in this class already. So standard assembly, standard boundary conditions, and then solution. Okay. The only thing that you don't have to worry about here is that you don't have to worry about adding in the loads like what we did before, just because those are kind of automatically baked into the elements forcing vectors. Okay. So the only boundary condition that you have to add in manually are just the constraints or the Dirichlet boundary conditions. All right, any questions on this example here? Okay, good. All right, so that's finite element formulations in a nutshell, right? So we've taken kind of a long journey to get here, right? But basically what we have now is we have a system that's able to take a differential equation, granted it's a 1D differential equation, and convert it into a finite element problem, a finite element problem involving matrices and boundary conditions and things like that, using this method. Okay. So now you can basically take this method and solve any 1D differential equation in a finite element form. Okay, so it's kind of a combination of everything we did in the first half of the course combined with what we know now about differential equations. Okay. Where we're going to go from here, or the only place we can go from here, is we're going to apply the same methodology to 2D systems, right? So we're going to start looking at differential equations for 2D problems, and so problems involving X and Y, and we're going to see how that modifies our process here, okay? But we're going to start that next week. Okay? But that's just kind of give you a sneak preview of where we're going to go. For the rest of the time today, I want to go over kind of a very important concept known as Gauss quadrature. So it seems like a little bit of an aside, but it's something that's going to support us kind of moving forward. Okay. Okay. So Gauss quadrature belongs to a family of methods known as numerical integration. And what you'll see is that Gauss quadrature is going to be a really important tool for us. Maybe not so much in 1D, because we can do 1D integrals pretty easily. But it's going to be a really important tool for us in 2D. But before we know the 2D part, we have to learn the 1D. Okay. So what is the point of Gauss quadrature? Why do we want to do this, right? So let's kind of take a step back and look at kind of everything that we've done so far, right? So the last example that we did, it kind of spanned, at this point, it's kind of basically spanned 2 whole lectures. But a big part of that example and a big part of finite elements in general is evaluating all these different integral expressions. And so what you can say just in general is that, finite elements, you just have to evaluate a lot of integrals. That's just how it goes. Okay. If you think about the problem that we just did, right? So the problem we just did was a fairly simple problem. We had 2 elements, right? In each element, we had to evaluate at least 2 integrals, right? So we had to evaluate 1 integral for the element stiffness matrix and 1 integral for the element forcing vector, right? So, if you consider, the amount of integrals you have to do equal to the number of elements times 2, right? If you think about a typical kind of a practical finite element mesh, maybe something that you did in ANSYS, right? So an ANSYS mesh could have anywhere between, 10,000 to 20,000 elements, and that's on the lighter side, right? And so for a 20,000 element mesh, that means you're evaluating 40,000 integrals. So it's something you have to do kind of constantly, okay? And so, of course, when you have to do something that much, it kind of necessitates that you kind of automate the process, or you have a way to kind of make it easier on yourself to evaluate these things. Okay? But actually, the most difficult part that a computer struggles with the value in integrals is actually doing the antiderivative part. Okay? So what do I mean by antiderivative? Let's look at how a typical integral is solved. Right? So let's say we have an integral from x1 to x2 of some function x, okay, dx. Right. And so if we were to evaluate this integral in kind of a classical way, we would perform the antiderivative on the function f, right? So we get some function big F of x, okay? And then evaluate this big function f of x from x1 to x2. And so the evaluation of the integral will be big F of x2 minus big F of x1, okay? Where the relationship between big F and little f is such that the derivative of big F with respect to x is equal to little f of x, okay? But it's that first step in the process of, taking some function f, and it can be a generic function f, and then, taking the antiderivative to get your function big F of x, okay? And so how do we do that process normally? Well, we've at this point, you guys have taken, 5 or 6 different classes in calculus or calculus adjacent classes. And so, you've seen a lot of it up to this point. And so it's something that you can do at this point just based on kind of pattern recognition. Okay. But in a traditional computer code, I know things are changing with AI and everything like that. But in a traditional kind of computer code that you would write in like MATLAB or C++, right? This process is actually very difficult. And so it's not something that you can just kind of code up very easily, okay? So this kind of necessitates kind of a different way to evaluate our integrals, or it leads us to ask a question, is there another way we can evaluate our integrals that's a little bit more computer friendly or computer code friendly? Okay. Turns out there is. And in fact, there's actually lots of different ways to evaluate these integrals. And they're all kind of based on kind of a very kind of maybe a concept that you haven't heard from in a very, very long time. So think back to kind of when you first learned about integrals before, right? The integral of a function, probably the first thing that you learned is nothing more than just the area under the curve. Right? And so we have some function here, right? Like this, right? If we take the integral, right? What we obtain is the area of the shaded region under here, right? So the area between the curve and the horizontal axis. Right? When you first learned this concept, or when this idea of integration was first posed to you, probably the first thing that you learned was something called a Riemann sum. Right? It's a very kind of geometric way of kind of evaluating the integral. So instead of performing the antiderivative and things like that, what you can do is you can fill this space with a bunch of little tiny rectangles, right? Where the rectangles kind of form the shape of the function itself. Right? And then what you would do is you would compute, even though you couldn't compute the area of kind of a generic curve, but you could compute the area of a rectangle, and then you can add all those things up together, right? Okay. So now your integral expression, integral from x1 to x2 of f of x dx, instead of being an operation in calculus, now it's an operation in geometry and algebra, right? So now what you can say is that this integral is equal to f at x1 plus f of x2 plus f of x3, yada, 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 okay? Or x1, x2, x3, those are the locations of all the rectangles, okay? And most importantly, you're going to apply a weight to each of these terms, okay? So it's going to be like, we'll call it W1, W2, W3, okay? And the Riemann sums, those weights are usually correspond to the width of the rectangle. So, if I were to kind of break this down here, the W1, W2, W3, those are the weights, or what we call weights. And then the f of x1, f of x2, f of x3, this is the integrand evaluated at certain select points. And so our integral expression here now becomes, or the way that we evaluate this integral is now a weighted sum instead of a calculus operation. That's basically the name of the technique. So a Riemann sum is nothing more than just what we call a weighted sum type of method. Okay. It was a very geometric way of evaluating integrals, and probably for actually I don't know how it is now, but when I was first learning calculus as a in my first year in college, that's how I learned it. Okay, that you just take a weighted sum of your function. All right. Any questions on this? Okay. So how does this relate to Gauss quadrature, right? So, I told you that this section was about Gauss quadrature, but then we started talking about Riemann sums. So Gauss quadrature is based around the same idea. So the idea with Gauss quadrature is that we're going to evaluate our integrals with a weighted sum. We're just going to do it in a slightly more intelligent way than the Riemann sum. Okay? Okay. The difference between Riemann sums and Gauss quadrature is that Gauss quadrature aims to be efficient. Okay. And so in order for Riemann sums to work, you need a ton of different points, right? And so probably what you learned back then was that the more points or the more rectangles that you utilize, the more accurate your Riemann sum is going to be. Okay. But Gauss quadrature ain't got time for that. So we ain't got time to evaluate the function, 20, 30, 40 times, right? Gauss quadrature is like, I want to evaluate the function once or twice, and I want to get an accurate result from that. Okay? Okay. All right, so here's how it works. And so the base form of Gauss quadrature only works when your integration bounds are between -1 and 1. Okay? And if that's the case, and I know that seems very limiting, and I realize that, but there is actually a way to kind of expand Gauss quadrature to any integration bound. But we're going to learn kind of the standard way first. Okay. And then from here, you can choose how many Gauss points that you want, or how many function evaluations that you want to do. Okay. And so naturally, the more function evaluations that you do, the more accurate your integral is going to be, but it also kind of increases the cost. Okay. So you can consider kind of this trade-off between kind of quickness or speed versus accuracy. Right? The number of function evaluations that you can choose is called the number of Gauss points. So let me kind of show you the table here. All right, so Gauss quadrature actually can be extended to more than 3 Gauss points. In fact, there's theory that extends to dozens of Gauss points. But at that point, it just kind of becomes just a mathematical curiosity. So what's useful for us is Gauss points equal to 1, 2, or 3. Okay. So we're going to look at three different types of Gauss quadratures, right? The 1-point rule, the 2-point rule, and the 3-point rule. Depending on the rule that you're choosing, you know, the 1-point, the 2-point, or 3-point rule, it's going to change the locations of where you're going to evaluate your function. Okay. So for example, right? So for one Gauss point, we're going to evaluate the function at x is equal to 0. Okay. If you're going to evaluate it at 2 Gauss points, okay, the first location is going to be at -1/√3, and the second one, sorry, this is x1, and then x2 is going to be at a +1/√3. Okay. And then if you do a 3-point rule, x1 is going to be a -√3/5. X2 is going to be at x is equal to 0. And then x3 is going to be at a +√3/5. Okay. Okay. And the last column that we have here are the weights. Okay, so these are the weights that you're going to find the weights. Okay. All right, so for the 1-point rule, we only have one weight, and so that weight is just going to be 2. Okay. For the 2-point rule, both the weights are 1. And then for the 3-point rule, we have 5/9, 8/9 for the middle point, and the weight for the third point is 5/9. Okay. So basically what this rule is saying is that, you know, we can evaluate integrals by just evaluating the integrand at these very select points, right? It seems like voodoo magic at first. And so and so I think the last thing we're going to do today is to kind of show you an example of how this works. Okay, so let's take this integral. So let's take the integral from -1 to 1 of 3x² - 2 dx. Okay. And let's evaluate this integral using a 2-point rule. Okay. So to use Gauss quadrature, you know, you're going to take your integrand and you're not going to take the antiderivative. Okay? You're just going to take the function as it is. Okay? And so using the 2-point rule, we're going to evaluate it at 2 locations. So we're going to evaluate it at x1 is equal to -1/√3, and x2 is equal to 1/√3. Okay, so let's do the first Gauss point first. Okay. And so the first Gauss point, we have 3 times x², so that's a -1/√3 squared minus 2. Okay, plus oh, we forgot our weights. Okay, so the weights, remember, in the Gauss quadrature is 1. Okay. And so then we have the same function evaluated at the second Gauss point, which is 3 times 1/√3 squared minus 2. So this right here is W1. This right here is F at x1. This right here is W2. And this right here is F of x2. Okay. So our weighted sum here is W1 F of x1 plus W2 F of x2. Okay. That's all we're evaluating here. So we're just evaluating the weighted sum of the integrand at our 2 select points. Okay. Okay, so let's evaluate this. And so, we can just evaluate this algebraically. And so we have a 3 times a minus 1 over root 3 squared. So minus 1 over root 3 squared is just 1 over 3. And so that first term there is 3 times 3 over 3 minus 2, which is a minus 1. Okay. Times 1 plus 1 times. We have a 3 times 1 over root 3 squared. So that's 3 over 3, which is 1. Minus 2 is a minus 1. Okay. And so what we get from this integral is minus 2. Okay. And that's the integral, right? And so we did this integral without having to take the antiderivative 3x squared minus 2. Okay. Now I know what you're saying. This seems like voodoo magic, right? There's no way this actually works. Let me prove it to you. So let's evaluate this integral in the normal way and then see if this is the same thing as what we got up there. Okay. So evaluating this integral in the normal way, we're going to take the antiderivative of the integrand. Okay. So we're going to take the antiderivative of 3x squared minus 2. So that's an x cubed minus 2x. Okay. We're going to evaluate this from x is equal to 1, or x is equal to minus 1, and x is equal to 1. Okay. And so that's equal to 1 cubed minus 2 times 1 minus 1 cubed minus 2 times minus 1. Okay. Okay. So let's go ahead and evaluate all these terms here. So we have a 1 minus 2 minus a minus 1 plus 2. Okay. So of course here we have a minus 1 minus a 1. Okay. And so this is equal to minus 2. Right? So by using a completely different way, a completely different method than what we usually do for integration, we were able to get the same exact thing. Now, I know what you're all thinking, I just cherry picked this example. Of course it works out because I chose it, right? Try it yourself. Try any kind of random function that you can think of and try applying it for the Gauss rule. Now, there is a limitation to Gauss quadrature, right? It's not magic. And I'll tell you kind of the reason why we use Gauss quadrature for finite elements a lot. Okay? Okay. The reason Gauss quadrature works so well in these kind of situations is that Gauss quadrature works super well for polynomial integrals. Okay. And so polynomials are your typical functions of x, and so x squared, x cubed, x to the fourth, right? So when your integrand is a polynomial, Gauss quadrature works exceptionally well. Okay, granted. So it actually gives you an exact solution if the highest order of the integrand, or the highest order of the polynomial, is less than or equal to the number of Gauss points that you choose. Okay. All right, question in the chat. So how does it perform for exponential logarithmic integrands? it still performs well, and so it's not going to give you a completely erroneous result. It's just that you probably need more Gauss points in those situations. So, so even we're going to come across situations in FE8 where we are going to have those either exponential or logarithmic or sinusoidal integrams. We're still going to use Gauss quadrature, with the understanding that it may not work as well. But for the most part, for most of finite elements, our shape functions are polynomials, our variations, our body forces are often polynomials, and so we just see a lot of polynomials in finite elements. So that's why we picked Gauss quadrature. But definitely try that. So definitely try out different polynomials. Try out different things, and you'll see that Gauss quadrature will have your back. Okay? All right, so that's all we got time for today. And so when we come back on Thursday, there is a little bit more to Gauss quadrature that I want to talk about, which is how to apply it when your integration bounds are not -1 from 1. So there's kind of an extra step, an extra change of variables that we have to do in order to get that to work. But we'll talk about that on Thursday. Okay. The other thing we're going to do on Thursday is we're going to talk about how to implement these finite element solutions in MATLAB. Okay. All right, so thank you guys for coming today. I hope you guys have a good rest of your evening, and I will see you on Thursday. Thanks, guys.
You have a good break?
I did.
Yeah.
Yeah, I visited a friend. I haven't seen this friend in over a year.
Oh, nice.
She lives up in Fresno.
Uh-huh.
So she moved to Fresno and she had a kid close about the same time.
Wow.
So we saw her, we met her baby, and so he's like 14 months old. So
Wow,
he's adorable.
awesome.
Yeah, we got caught up, stuff like that. So it was really nice.
That's good. That's good.
How are you? Good break?
Yeah, the comprehensive exam was intense.
Oh, yeah.
Yeah. So I'm glad it's over, but we'll see if I have to retake it. It's mayoral said next week maybe.
Okay.
19th.
Cool.
We'll find out. So
Sounds good.
yeah.
Okay.
Thanks, Professor.
Yep. See you guys.